Welcome to this screencast on logic. In previous screencasts, we have discussed compound statements and constructing them using logical operators, and also discussed determining their truth values by looking at truth tables. In this screencast, we will discuss what it means for two statements to be logically equivalent to each other. Let's take a look at the following example and complete the truth value for each of these statements. If you want to, pause the video now and complete the truth tables for each of these statements on your own. It is fairly easy to complete the truth tables for each of these four examples, so I'll do it quickly here, and now we see the truth values for each one of these. What we want to notice is that for example A, the truth values are false, true, true, and true, and for example C, the truth values are exactly the same as that. What this will mean for us is that the statement in example A is logically equivalent to the statement in example C. Looking at the truth values of the remaining two statements, we see that they also have exactly the same truth values. And this, of course, will mean that the example in part B is logically equivalent to the example in part D. So what does it actually mean for two statements to be logically equivalent? Here's the definition. Two statements x and y are logically equivalent if they have the same truth tables. And we write a symbol that looks like an equal sign, but it has three parallel lines in it. And we read this statement here as x is logically equivalent to y. If we look back at the previous example again, what we said was the statement in part A is logically equivalent to the statement in part C because they have the same truth values. So we would read this as not P and Q is logically equivalent to not P or not Q. And this is the first of two properties known as De Morgan's law. In general, if P and Q are statements, we see in the first part of De Morgan's law that not P and Q is logically equivalent to not P or not Q. In the second part of De Morgan's law, it's the other two parts from the previous example, and we see that not P or Q is logically equivalent to not P and not Q. Notice that as you distribute the negation in each part, the conjunction changes to a disjunction, or vice versa. In a similar manner, just using truth tables, we could easily show many different logical equivalencies. Here are a few more. The first two parts of this theorem tell us that conjunctions and disjunctions are commutative. The order in which we take the conjunction or disjunction does not matter. P and Q is the same thing as Q and P, and P or Q is the same as Q or P. We also have associativity of conjunctions and disjunctions. Now let's look at two new terms associated with implications or conditional statements. We have a conditional statement, P implies Q. The converse of this is Q implies P, changing the conclusion to a hypothesis and the hypothesis to a conclusion. The other new word we want to look at is contrapositive. The contrapositive of P implies Q is not Q implies not P. So we're switching the placement of the P and the Q, and we're also negating the two statements. Let's look at these within the context of a specific example. Let P be the statement, I don't clean my room. Let Q be the statement, I don't get dessert. The conditional P implies Q is simply read as, if I don't clean my room, then I don't get dessert. The converse of that is Q implies P, and we would read that as, if I don't get dessert, then I don't clean my room. And finally, the contrapositive of P implies Q is not Q implies not P. And we read this as, if I get dessert, then I clean my room. Consider pausing the video for a moment and decide whether or not any of these statements have an equivalent meaning. After a little thought, it should be pretty easy to see that examples A and examples C have the same logical meaning. If I don't clean my room, then I don't get dessert means that if I did get dessert, I must have cleaned my room. So parts A and C seem to have the same meaning. On the other hand, part B seems to imply something different. As it turns out, this is a correct observation. A conditional and its contrapositive are logically equivalent, and here we see it in the form of a theorem. P implies Q is logically equivalent to its contrapositive. Not Q implies not P. However, the converse is not logically equivalent to the conditional, and both of these can easily be shown again by using truth tables. Not only is a conditional statement equivalent to its contrapositive, but one can also show that a conditional is logically equivalent to a disjunction. In other words, a conditional can be rewritten as a disjunction, since P implies Q is logically equivalent to not P or Q. The negation of a condition, not P implies Q, is logically equivalent to a conjunction, P and not Q. Again, both of these can be proven by just looking at the truth tables for each of these statements, and I encourage you to do this on your own.